So, good evening, everyone. So, in today's lecture, we will continue this session. So, as we discussed earlier in this session, that all the introduction, what is RIS and why choosing the best phase for across the reflective elements. The existing studies divided into two things. One in which we have a continuous basic for each optimization, and another one is as where we have discussed the restricting phase shifts. Okay, and we establish the result that is in the terms of order of an algorithm. Okay, for this one. Okay, the proposed algorithm are in the geometrical forms, geometrical interpretation. It was observed in the paper 1, paper 3, and paper 4, where we focus on the binary beam forming case. Either we have to choose phase shift as 0 or pi, or a k array case where each phase having the phase shift will be k discrete form. Okay, so we visualize, so we try to visualize all the things in a unit circle, and the point moving around the unit circle capture the different beam forming decision. Okay, the essential power of the geometric method arises from the observation that although the number of possible combinations for the phase shift go exponentially, but there must be a some linear linear number of unit circle that can possibly contain the point of optimal beamforming. Furthermore, the utilities of these are can computed in linear way. Okay, so to try out the possible arc and pick the best and recover the optimal phase. Okay, the existing work on the global optimal, the existing work consider the global optimum for that discrete beamforming. Although the IRS technology was intensively explored by many of the in many literatures, and it is with using the different complicated system model. Okay, the simple point-to-point model is still far less understood. Okay, the common practice is to solve by relaxed continuous beamform the problem by standard optimization. Okay, and the semi-defined relaxation based on the minorization and maximization for the relaxed continuous beamforming problem. Okay, so but these method incur the exponential time complexity and provide the limited insight. For the practical approach, the best result so far in this literature is to obtain the approximation ratio for the global optimum is cos square pi by k terms. Okay, and two optimal signal to noise ratio. Okay, and in different values of the phase shift can take on. Okay, and further it improved to this one 0.5 to 0.5, this one 1 plus half of something. And furthermore, it is worth mentioning the connection to the quadratic program like X transpose QX, and the author already observed the discrete IRS being forming problem is an NP hard. Look, that NP hard, it is something that is very difficult to solve in general, but can be efficiently solved under the condition. So each entry of the X selected, so and now we can say that each entry of the X is selected from the binary set of 0 or 1 of rank, that is rank for that quadratic function is less than is equal to 2. Actually, the quadratic time algorithm proposed in the paper number 15 for the binary IRS beamforming is a direct application of the quadratic program methods that is used in a paper number 17. So binary quadratic program is a direct binary quadratic program without a rank constraint can be solved polynomial time as well as. Nevertheless, a generic array discrete QP remain open problem. Okay, the proposed algorithm can be recognized. The proposed algorithm can be recognized as a linear time approach to the spatial K for the K array QP. Okay, So, so now we have to see the system model. Consider a wireless communication is a aid of an IRS. Okay, assume that IRS comprise of n reflective elements and the transmitter and the receiver having one antenna of each. So we use H naught as a complex to denote the direct channel from the transmitter to receiver. Okay, and HN is also complex from nth transmitter to nth reflective element, and H12 is connect from channel from the nth higher to receiver. So the cascaded reflective channel HN is an also complex associated with the nth reflective element, and we will turn this one as a multiplication of like it is a reflective element. Okay, and this one is a transmitter through which we it goes. So this one is Hn of I, this one, and this one is H2 of N. Okay, so in the reminder paper, the direct and the reflected are the frequently written in the full form. So in the reminder, the paper in this paper, we see a direct and the reflected are frequently written in the polar form. So Hn, beta n. So Hn term as a beta n e the power j alpha n. Okay. 1 second. So Hn was and this is the magnitude that is greater than 0, and the alpha is a phase that we choose from the 0 to 2 pi. Okay, and for in particular we see that magnitude is still greater than 1 occur if this condition is happening, occur if the IS can be amplified this reflection. So it is an important point to be noted that if that is if we represent Hn is equal to in the polar form is equal to beta n e the power minus j alpha. Okay, and this beta is known as the magnitude that is simply greater than 0. If beta n is greater than 1, so it occurs only when IS can amplify the reflection. Okay, assume that the channel phase a channel phase, this one is a channel phase alpha n are uniformly distributed. Moreover each reflective element n induce the phase shift of theta and it into the reflective channel Hn, which take on the value in a prescribed discrete set. Okay, so and this phi k is a part of omega 2, omega 3, omega 4, omega like k omega. Okay, and omega is termed as a 2 pi by k. So for the transmitted signal that is the also part of a complex number, and the received signal is a set of a complex number. So we call as a what we get a received signal. So received signal is equal to the direct gain from the transmitter to receiver one. This one is direct term, and this is summation of n1 is transmitted reflected from the iris element, all the summation of Hn and all the phase of something. And this is Z is a noise, and we can say it is a complex noise, complex Gaussian noise. Okay, and an SNR can be computed by SNR is known as signal power by noise power. So SNR is equal to is signal power to noise power. So is signal power to noise power. So signal power, we have to subtract all the noises. Okay. So if it's term into this one, P of something, this one. Okay. So baseline SNR. This is the baseline SNR. Okay. We all write everything in the beta form, as we know that Sn is equal to beta of something, beta n e to the power minus j alpha n. So this part is written here. This part is written here. Okay, 1 second. The baseline SNR and baseline SNR versus SNR can be written as follow. Okay. So this part is clear. This is smooth one. I need to use paper napkins. Okay. Mm, so the to quantify the performance gain of IRS, we can introduce the notion of SNR boost. SNR boost is simply SNR by something. So this one. Now we consider the problem. Now we consider a problem to finding the optimal IRS beam forming in theta in the term of vector that yield the highest. That yield the highest. So we have to erase this part. What's happening? I don't know. Um, so wait for 5 minutes. So welcome back. So understanding the part of everything. Okay, where we are. So we are at this person. So in figure one, we can clearly And we clearly see that it is an optimal set of either theta 1 is greater than theta 2 is equal to 0, or theta 1 theta 2 is equal to pi in this example. And but we can end up with theta 1 by end of choosing that theta 1 is equal to 0 to theta 2 is equal to pi. Each h of n is rotated by the position h naught, which gives a fairly good performance. So SNR boost. So SNR boost simply a maximum of that one. Okay. So we assume that all the channel information is available. We assume that all the channel information is available in above problem. The optimal value at uh, in the above problem, the optimal value of the particular theta n heavily depend on how theta m, that is m is not is equal to n, is chosen. It seems to be in inactable to direct coordinate all these theta n because the size of solution space is the space into multiply this is exponential in n. Nevertheless, rest of the paper show that the problem can optically solve using the it seemed to be interactive directly coordinate all theta n because the size of the solution because we get the size of the solution space will be 5k into 5k. It is exponential in the term of n. Nevertheless, the rest of the paper show that nevertheless the rest of the paper show that the exponential exponent so that the problem can be optimally solved in a linear time expectation expectation. Okay, so this is the system model look like. Okay, the proposed methods, what are the proposed methods that we use? Okay, proposed method we discussed earlier, that is a geometrical interpretation. So geometrical interpretation of this discrete beamforming. So uh, the problem in it we can visualize with the complex plane graph where every channel element corresponded to a two-dimensional real vector. Okay, corresponding to two-dimensional real vector. Applying these phase shift theta n to the hn can be viewed by rotating the vector hn in a counterclockwise by an angle of a theta n. Okay, so suppose on the problem we see that we have to do this problem in a linear expectation. Okay, because our solution space is in the exponential exponent. Okay, the geometric interpretation of the discrete beamforming can be visualized. So the problem can be visualized with the complex plane where every channel phase shift theta n to that hns can be viewed by rotating the vector hn in counterclockwise by an angle of theta n. Okay. Recall that rotation must be discrete. Recall that rotation must be discrete because of the constraint that theta n is a 1 second. So we can see that theta n is a part of that group of 5k where all the thetas we have. So we aim, so our aim, so we aim we aim to coordinate the rotation of this h1, h2, hns, so that the magnitude of that vector addition is maximized. Okay, so so the problem we have, we have to visualize in the complex plane, and for the average channel hn, which corresponding to the two-dimensional real vector. Okay, applying the phase shift to the all the to the hns, we can we view as a rotating the vector hn in a counterclockwise by the angle theta. Recall that the rotation can be discrete because of the constraint that theta n is a part of psi k. Okay, so our aim to coordinate the rotation so that our aim is to coordinate the rotation so that h1, h2, h3, hn, so that the magnitude of their vector is maximized. Okay, thus if theta 1 star, theta 2 star is the optimal solution, and then vector addition is seem to like a, and the vector addition seem like a h naught in the summation of this one. Okay, okay, and has a maximum length. For that rotation of is having the maximum length of this one. So we write the normalized g in the term of this one, and this is the reference vector. Is mu is the reference vector. Notice that the vector h naught is fixed. H naught is fixed. A naive idea for maximizing, the naive idea is for maximizing the modulo of g is to rotate every hn to the closest possible position of h naught in a complex plane. Oh, so we so our target, our naive idea is to maximize the mod g value. How we do? We make every hn value possible closest to the h naught of that complex name. Is namely as a closest point projection that we term as a CPP. Okay. However, every CPP is a suboptimal and can be yielded. However, however, CPP is then suboptimal and can be yield quite bad result. Okay, illustrated in figure 1. The reason is that H naught may be considerably derivated from the mu, in which each aligning Hn with H naught cannot contribute much to the magnitude of overall addition. Okay, rather it is always optimal to rotate. Rather it is always optimal to rotate the Hn to the closest possible position to mu, and as stated following lemma. Okay, we have noticed that h naught is fixed. A naive idea is to maximize the modulo of g. So we have to rotate all the h's to closest to the h naught in a complex plane. That is, this term is known as the closest point projection, CPP. And CPP is a suboptimal. It is not the optimal. It is suboptimal and can be yield but bad result. And the reason is that h naught may be considerably derivated from the mu, in which case aligning hn with h naught cannot contribute much to the h naught is not that much contribute in the magnitude to the overall vector addition. Rather it always be an optimal to rotate hn to the closest point to mu, as stated following lemma. Okay, so we have to take 2 to 3 minute break, and we have third page and fourth page. Third page we have to take break.